In this video, we will see how to do some elementary computations with differential forms using Mathematica's intrinsic functions. We will start with the use of the function tensor wedge that will allow us to compute the wedge product of two differential forms. Let's see the Wolfram documentation for this function. So we type here tensor wedge, and it takes us directly to the page that describes the usage of tensor wedge. You can see the details here. So tensor wedge takes two arguments, which are differential forms, and computes their wedge product. If we supply components, it will give us the components of the wedge product, and later we will see how it handles abstract definitions of differential forms. You may type the wedge product using the tensor wedge symbol. Be careful, it's not the same as the ordinary wedge. The ordinary wedge is typed by typing escape, carré escape, and that gives us the wedge product. It looks exactly like the tensor wedge product, but it does not compute the tensor wedge operation on the two forms. For that, you have to type escape t carré escape, or write backslash tensor wedge as it is shown here. So let me show you. I press escape. I see this sandwich character here, and then I press T, then wedge. You see that I obtain information about this symbol here, and then press escape again, and the wedge symbol is formed by this sequence of keystrokes. So to do some sample computations, let us first define the dimension of space to be 4. So the symbol D is set equal to 4. And we will define two forms, A and B, which are declared by the function array here. And array applies the function subscript with the symbol small a on the two indices here that range from 1 to d. So we will obtain the symbol a with two indices I and j ranging from 1 to d. And similarly for b, the same thing will happen, but using the symbol b instead of the symbol a. We will also declare two one forms by applying the function subscript with one index on the symbols omega and lambda. We will use some assumptions to help Mathematica do calculations. So A and B will be handled as arrays with two indices, real elements, and being antisymmetric with respect to all of their indices. And omega and lambda are arrays with indexes with one index ranging from 1 to d and real elements. So let's see the effect of doing this declaration here. We evaluate the cell. So you see that the two form A has matrix elements A11 up to A14 and A11 up to A41, and we have this 4x4 matrix of elements. Similarly for B, whereas omega and lambda are simple lists that can be shown as column vectors here. But as we know, the two forms A and B are antisymmetric, and we don't see that this way. So whenever we want to apply the antisymmetrization property, antisymmetric property of the two forms, we will apply a rule that we will define now. So you see here we create a rule which is a list of rules, and each rule here takes an element aij to minus aji for indices ranging from 2 to d and j from 1 to I minus 1. And the rules also take the diagonal elements to 0. Similar rules are applied to the two-form B, and because we want the rules to be just a list of objects, we flatten this list, because table here creates lists of higher depth. So let's see what happens if we apply this newly created rule to the two forms A and B. We evaluate the cell. So you see now that A has elements that when seen as a matrix, they have a non-trivial upper triangular part, A12, A13, A14, etc. And the lower triangular part is minus the upper triangular part. And the diagonal is set equal to 0. Similarly, the same rule is applied on the two-form B. Now here you see the explicit form of the rule as a list, and understand why it has this effect. So let's compute now a wedge product. So we'll compute the wedge product of the one form omega and the one form lambda. That will give us a two form. So we evaluate this cell. So you see that tensor wedge gives us an object which is a symmetrized array. That is a more economical way of storing the information of the wedge product, because there are many zero elements here that are not needed to be stored. And if you want to manipulate this as a list, you have to normalize it by applying the function normal. So if you apply the function normal here, the two form here is shown as a list of lists of components. And for an even more convenient view, we can apply matrix form and view this two form as a 4 by 4 matrix. So you see that this is indeed a two form with all its elements being, all its components being antisymmetric. So the same result would have been obtained by using the symbol tensor wedge instead of the function tensor wedge. And then expressions are easier to read. Okay, let's see how to compute two forms of higher type. So omega is a one form, A is a two form, and we will compute this by applying both the normal function, so that we can see that as a list, and matrix form to have a more convenient visualization of its components. So you see now we obtain something bigger here. Let's see how it looks. First of all, because now this is a three form, we obtain matrix form gives us a matrix of vectors. So you can see how the components are arranged, and you also see that the results here do not apply the antisymmetric properties of the two form A. You see that we have here A12 minus A21, which this is simply 2 times A12. So if we want to see this result, but having only the independent components of the two-form A, we have to apply the rule that we have created above. And now you see that the result contains only the independent components of the two-form A. We can select the non-zero components by using the function SameQ. SameQ returns true when the expressions x and y are the same. And because this is done quite often, Mathematica has a shorthand for this function, which is represented by 3 equals instead of 2. So this is not the same as being equal, but the symbols are examined as being the same. So let's see how to select all the non-zero elements. First of all, we compute the list of all the components of omega wedge A. We normalize the wedge product. We apply the anti-symmetrization rule. And because this is a list of lists of lists, then what we will do is we will flatten this list and obtain a list of depth 1. So when you do that, you see you obtain a list of all the components. So now we can use the function select to select all the non-zero elements. And as you remember from previous videos, select takes here a list as its first argument, and then it applies on it the function that we put in its second argument. So the function that we will put must be a function that has a logical result, which when applied to each elements of the list of the first argument will give us either true or false. So select will construct a list where the function here will evaluate to true on an element of the list on the first argument. So the function here you see is a non-name function. That is, the symbol for that is the English symbol for and then this is the body of the function, where the hash is the argument of the function. So when this function is applied on this list that you see here, then for example for the first element of the list, the number 0 will be substituted. So 0 is the same as 0, that will evaluate to true. The negation of this will give false. Therefore the 0 element here will not be added to the list that select constructs. But when we get to this element here, for example, this expression is not the same as the expression 0. So all these things that I have selected here will be substituted in the place of the hash and compared to 0. And this will evaluate to false. The negation of false is true. Therefore, this element will be added to the list that is constructed by select. So we evaluate the cell here, and you see that indeed we obtain a list that contains only the non-zero elements of the three-form omega wedge A. And we can view it in a more convenient way by applying the function column on this list. So we see all the non-zero elements here arranged in a column. Now, of course, this result gives us all the non-zero components, but it gives us no information to which indices of the three-form omega wedge A they correspond to. if I want to make a map of the indices with non-zero elements and their values, I have to work a little bit harder. So let's see a way to do this. First of all, I construct a list, which I call list with small letters, which contains all the components of the three form after applying the anti-symmetrization rule. Then I construct a list here with a function table and see what it contains. It contains a list of lists of pairs where the first element here is the string omega wedge A subscripted by ijk. Then the second element of that list is the value of the component, of the corresponding component of omega wedge A. So I do that for all values of I, j, k ranging from 1 to d. So that contains, that's a list of depth 3. Now I take this list and I want to make a list of those pairs. So I use the function flatten, but I use it only up to level 2, so that we'll obtain a list of pairs. So let's look what this will give us. So let's call this list. And then construct this table. So you see here we obtain a list that has the same structure as the three form, but instead of having just the components, we have pairs that has the name omega wedge A and then subscripted with by the corresponding indices. Now when we apply flatten on this list of lists, sorry, here, you say that I obtain just a list, but it's not very useful because it does not group together the name of the component and its value. So this is why I ask flatten not to go all the way down, but go up to level 2. And then you see that I obtain a list of pairs of the name of the component and its value. And then I can use the function select, and I have to make a small modification. I have to check whether the value of the component is 0. So now select here will have a list that has those pairs. So I should not compare the full list to 0, but only its second argument. So you see that here I use hash. Now hash is a list of those two expressions, the name of the component and its value. And then I select the second member, which is the value of the component, and compare it to 0. So whenever the value of the component is 0, it will not be added to the list. Otherwise, it will be added. And you see, now the result here, I have this list of pairs, and each pair has a first member here, which is the name of the component, omega wedge A, subscript 1, 2, 3, and then the value of the component. So I can see the result and use it in whatever other expression I want to use it. Now let's make some simple checks of those calculations. we know that the wedge product has a graded anti-commutativity property, which when applied to the wedge product of a 2 form with a 1 form, the result should be commutative with respect to the change of the order of taking the product. So we check this against an array that has all its elements to be equal to 0, and this turns out to be true. Now let's see how this works. That is the left-hand side here. You see it makes the computation and returns 0 for all the components of this tensor. Now the constant array here has constant value of 0 for the 3 indices ranging from 1 to d, and it contains also only 0 elements. So when we compare those two expressions, we see that they are equal, and this is the reason why this expression returns true. Let's play a little bit with higher order forms. So we take the wedge product of two forms, and here we have selected the non-zero elements using a similar expression that we used with the 3 form before, and this is the result that we obtain. Mathematica has also an intrinsic function called Hodge dual, and it allows us to compute the dual of differential forms. So if you go to the documentation center and you type here Hodge dual, you can find information about how it works and how to apply it in your computation. So let's see how it works. Now we have already defined the 2 form A. So we define the 1 form A1, which is A, but it is normalized and has the anti-symmetrization rules applied to it. And A2, that is computed by the Hodge dual, which must be which must act on an object that is a differential form. So the Hodge dual of A, normalized rule, and if you print the result, you see A as it was before. You see that we keep the upper triangular part of the components, and then the lower triangular part is equal to minus the upper triangular part. There are 0 in the diagonal, and then the dual form of this with respect to the Levi-Civita symbol is also a 2 form, and you see the upper and lower triangular parts are elements of A which contain the remaining indices. So we are in 4 dimensions, so there are 4 indices. So when we use 2 indices here, then there are only 2 remain, so we have only 1 possibility for this element here. So A12 will be replaced by A34, and the only thing we have to take care of is the sign of the permutation in order to put the correct sign here. And that is a work that we have seen how it can take some time to complete, and Mathematica does it here very fast. So we know from theory that the Hodge dual of a 4 form is a scalar in 4 dimensions. So we construct a 4 form by taking the wedge product of two forms, and we compute the Hodge dual, apply the anti-symmetrization rule, and the result you see is a scalar expression here that contains combination of components of A and B. Similarly, the Hodge dual of a 3 form is a vector. So if we compute the wedge product of A with omega, that gives us a 3 form, and its Hodge dual can be computed, normalized, apply the anti-symmetrization rule, and arrange the output in a matrix form, and you see that indeed we obtain a vector with components shown as here. We can do with Mathematica some limited abstract computations with differential forms without referring to their components. So let's see how it works here with some simple examples. Let's define some differential forms in 10 dimensions. So we have the symbol DIM, taking the value 10, the number of dimensions. And then we use assumptions to declare that Xi, Xi1, Xi2, and Xi3 are 3 forms in DIM dimensions with real components which are anti-symmetric with respect to all of their 3 indices. So it is here you see we say that the index 1 in place 1, place 2, and place 3 are anti-symmetric. And sigma is a 1 form. It's an array for Mathematica. It has DIM components which are real and, well, anti-symmetric. Doesn't. So we evaluate the cell. This is the result. So now we can compute expressions such as this. We can take the wedge product of Xi with sigma and sigma with Xi. That will give us a 4 form for each term. Now, if you evaluate this expression, you see nothing happens, although we know that the wedge product is graded antisymmetric. So, if you want to put the result in a canonical form, then you have to apply the function tensor reduce. And if you apply tensor reduce, Mathematica knows that Xi wedge sigma is minus sigma wedge Xi, and that will evaluate to 0. Similarly, we can construct linear combinations of forms and take the wedge product and construct more complicated expressions. Here is a simple example, of course. So Xi1, Xi2 are declared as 3 forms. A1 and A2 are not declared as anything, so they will be treated as scalars. But when we evaluate this expression, nothing happens. If we want it to be expanded, we have to apply the function tensor expand. And in that case, you see that we obtain the result after doing this simple, of course, computations. Mathematica also knows the dimension of the form since it has been declared above. So if you make an attempt, for example, to construct a differential form which is of higher rank than the dimension of the space, then it will know that this expression is 0. So here I make an attempt to construct a 12 form in a 10-dimensional space, and the result is equal to 0.